Good afternoon and welcome to our next segment of webinar series. Today we've got Mr. Dimitri Levitt, who's our Business Development Manager for Automation and Control and Industrial Internet of Things, and he's going to be presenting for us on the Australian market range of pressure sensors, and he's got some new things to show you, and I think some very interesting topic to cover here. So I'm looking forward to it, as I'm sure you are. I hand over to Dimitri now. Thank you.
Thank you, Mark, and hello everyone. So let's get started on the Australian market range of pressure sensors. Today we will discuss sensor output types, and along with the switching contacts, normally open, normally closed, IO link and where to use it and how it looks like and the main benefits of it. The pressure sensors that I've selected for the Australian market, i.e. these are going to be the sensors that we will hold in stock. So they'll be technically off the shelf and short lead times for customers. And the main goal of the webinar today is to make it easier for you to identify which off-the-shelf sensor you can offer to the customer very quickly, very easily. So let's get started. So here are some of the output types that are available with our sensors. This is not all of them that are available, but shows a majority of them. So you have like the analog range, which is the 4 to 20, 0 to 20 milliamps, 0 to 10 volts. These are all considered analog outputs. Then we have the switching or digital output style sensors, which have a relay output normally and a transistor output, and we will cover PNP, NPN, plus normally open, normally closed. And then we have the smart protocol or digital communication sensors, such as IO-Link, HART, CAN, etc. We also have more sensors from this, but this is just a general overview. And you see on the right of the screen some information about how the outputs are presented or in the data sheet. And on the left is just some wiring information. But today we'll focus on 4 to 20 milliamps transistor, 0 and IO-Link. But we'll also cover 0 to 10 volts. But the ones that I've highlighted, these are going to be the sensors that we're going to be keeping on the shelf. So now let's have a look at analog 4 to 20. So in general, this is one of the most common style outputs that you'll use, and it's used in the industry very commonly. And it's a 2-wire style sensor. So you can see here, 2 wires to wire the sensor and to power it and to get the signal out. There are different variants, and for special applications and things like that. So your customer will request that if they need it. Otherwise, generally it'll be a 4 to 20 sensor. Analog is better for longer distances because you have less signal losses, and one of the main reasons for a 4 to 20 milliamp is better than a 0 to 10 volt is say, for example, one is signal losses because voltage is more susceptible to noise. But if you have a broken wire, your PLC or control system will show 0 milliamps, effectively like an open circuit, so you can diagnose a sensor fault. On the right, you can see how a pressure range to a analog signal to like a 4 to 20 analog signal scales. So you can have a look at 60 bar, for example, will roughly be, say, maybe 14 milliamps, or 40 bar will be close to 10 milliamps, roughly. So that's how it converts how the scaling works. So 0 to 10 volt works pretty much the same way. The scaling is very similar. You can see but the signal starts at 0 volts. So when you have a broken wire and you try to identify this, you'll see 0. So you don't know if the sensor is seeing 0 volts or if it's an actual broken wire. But it's one of the main things for, say, diagnostics. The voltage sensors are generally 3-wire. You need to power the sensor, then you have the voltage signal that's generated. It is more susceptible to noise, and you have to be mindful of cable distances and things like that. So the main thing to notice is all the analog sensors you have to wire generally with a shielded cable, and you'll see coming up, but some, depending on certain applications, you may not require that. But best practice is to use a shielded cable. The other style of output is a switching output, and it comes in 2 forms, PNP and NPN. This just determines what the transistor or how the transistor works. If you want to find out more differences between a PNP and NPN, highly recommend Googling it. It is very low-level electronics, and generally it's not discussed in automation applications, but but you can't use one with the other. You have to know what the customer requires. Most of the time, it's going to be PNP. NPN is generally found in say Japanese style machinery or Japanese PLCs. Not to say that they can also have PNP. The main thing to notice here is with this style of output, or with our pressure switches that output a PNP signal, is the output voltage from the sensor to drive your load, which can be a PLC input or a relay, is the same voltage that you put into the sensor. A relay output, which we also have relay output pressure switches, and you can go through our catalog to find them. You can have a different voltage going through the contact to the different voltage you're using to power up the sensor. So generally used in like motor starter circuits or something like that. There may be a specific reason for it, but PNP is generally the more common one. So now another thing, so you have the PNP, NPN style output, but now we also have the switch contact, or like the contact output on how a sensor works. So there are two outputs, normally open, which is signified by NO, and normally closed, which is generally NC. And you can see on the left, the normally open contact is very much like a hydraulic spool or a valve. It's shown in the off state. In electrical schematic, it's always shown in the off state. So when there's no pressure being seen, or when this particular switch is off. So when the pressure sensor sees the set pressure, the contact will close and you will have voltage. The voltage will pass through the contact and go to your PLC or turn on a light or something. So normally open contact will close when the pressure setting is reached. And then, which is now counterintuitive or a bit opposite, is now you have a normally closed output where when the pressure setting is not reached, you're passing voltage through because you can see the contact is closed. So when the pressure setting is reached, that contact will open and then you will lose the voltage signal. So it just depends on how your customer wants to see this signal, or what their automation system and how it's programmed. Most of the time, we have sensors that you can do both, normally open and normally closed. So you can just have bipolar contacts just to recognize the changeover. Again, it's very application dependent, and your customer will specify what they prefer. Now, an interesting thing is how does a pressure sensor convert a real-world pressure value, like from the fluid, that is like hydraulic fluid, to an analog signal, to a 4 to 20 milliamp signal, so a PLC can read it. So here on the left, you see the pressure sensor with the fluid port. So there's a hydraulic fluid. You have the cell. The cell deforms dependent on the pressure. And on the cell, there is what we call a Wheatstone bridge. And as this physically deforms, and it's it's like micron, it bends in a micron level, so you can't physically see it. It'll deform, and then it'll produce a very, very slow signal, and we have to amplify it. So this picture here is with the electronics that are on board the sensor. So now we have the signal that's generated from the deformation. We need to amplify it. So now we've gone from real world, amplified it, we've converted it, we've amplified that signal. Now we've converted to a digital signal, which is now on a microprocessor. The reason we need to put this signal onto a microprocessor is because the deformation is just relative to the pressure, but there also could be heat could affect the deformation or the temperature of the fluid. So now we need to compensate that signal to give you the most accurate reading. So with a microprocessor, we can apply temperature compensation because there's a temperature sensor within the cell. So we can apply temperature compensation to the deformation and produce a more accurate result. Plus, because the deformation of the cell is not linear to the pressure sensor, we need to linearize the signal so we can have that straight edge that you saw, or that straight line that you saw with the like the pressure to analog conversion. So this is the main reason why we need to go from analog to digital. And now the fun part is to send it to a PLC. The PLC can't read this amplified signal, and it can't read this microprocessor communication at this stage. So we need to now convert this back to an analog signal, which is what we discussed, a 0 to 20 milliamps or a 4 to 20 milliamps or something of the like. So now we send this signal via a cable, generally a shielded cable, and then we have to terminate this cable into the control panel into terminals. So you can see how it gets terminated. But the one thing to notice here is we've done 3 conversions. We've gone from analog world to digital, back to analog, and now back to digital. So we've converted this signal 3 times. So when you're doing this, you have inaccuracies and you have losses. So the pressure that you might be seeing in the real world may not be the pressure, may have like a very, very, very minimal offset to what your PLC will read. But this is common for every single sensor that works like this. So now if we have a look at a smart sensor with a digital communication or something like an IO-Link sensor, we have the exact same setup. You have the fluid, you have the cell, you go through the same processes, the cell deforms, you amplify, convert to analog to digital, go into your microprocessor, you still apply the same temperature compensation, the same linearization, but the only difference is now you're not converting the digital signal back to an analog signal, you're just retransmitting that via a particular communication. And in this particular instance, we are doing IO-Link. So, and we only have one conversion. So we have now the most accurate representation of the real world pressure because we've only converted it once. We've done the corrections and now we're just transmitting it via cable. So we don't have any signal losses. We don't have any conversions back from digital to analog, then back on analog to digital and things like that. Plus there are some other benefits of IO-Link which are listed there. The main thing is you can have sensors that have multiple variables, pressure, temperature. Some sensors you can do pressure, temperature, and flow. And it can also do onboard processing and things like that. So if you find out more, I've got some information here. And the same applies if you have, say, a CAN-open sensor. Instead of IO-Link, it'll be a CAN-open transmission. So it's just for you to have a look at. And that is one of our IO-Link masters that will be available soon. So again, how does a IO-Link sensor system look like? You have the IO-Link sensor. You need to connect this IO-Link sensor to an IO-Link master. And then this IO-Link master can collect a number of sensors, and then it retransmits the data from the sensors via a field bus or a communication protocol to a PLC. And there are many communication protocols on the market, and it just depends on the customer that you're dealing with or what their site standard is. But Profinet is a very common one, Ethernet IP, Modbus TCP, EtherCAT. So there's a lot of very common protocols. And if you want to look up more there, if you have any questions, please don't hesitate to ask. To summarize IO-Link, IO-Link is a digital communication from the sensor to and from the sensor. So you can communicate to the sensor and receive data from the sensor, which is interesting because you can program the sensor, you can read faults and things like that. So very important to note. You should really only focus on industrial or stationary applications. The main reason is you need a stable 24-volt power supply and a DC power supply for IO-Link to operate correctly. If there is a slight drop in the power supply, you will lose this IO-Link signal. Because on mobile machines, the engine can fluctuate and the power or the battery power can fluctuate. So if you even have a 5% or a 5 to 10% drop in voltage, your IO-Link communication will die, and you will lose any signal from the sensor. The sensor has a processor for computing and smart functions on board, which is an interesting thing for data analytics and things like that. And it always uses an M12 connector. And the reason I say always and underline it is there is a standard for IO-Link manufacturers or manufacturers who are producing IO-Link sensors to always have M12. Unless they decide to change or deviate, that is the standard. So generally it'll always be an M12 connector. So now to our Australian market range of pressure sensors. These are the 5 sensors that I have selected for us to stock on the shelf, and I will go into each one of these. There is a copy of this presentation already available on our internal server, and if you want to go through them quickly, you can click on these links and they'll take you to the particular sensor. So now let's get started to the HPT1 1400S. So this is an IO-Link only pressure sensor. So the output of this sensor is eye-link. There is no analog, there is no digital output. It is just an eye-link sensor. So this sensor will only work with an eye-link master, and that is very important to note. So this sensor is a brand new sensor, which is why I don't have SAP numbers for this sensor yet, but they will be ordered and it will be kept in stock. And on the right, you can see just a brief blurb about the sensor, a datasheet extract. And if you click on this datasheet link, you will be able to open the datasheet for the sensor, because I have this datasheet linking to our internal server. So it does work. And if you click on it, you'll get the datasheet. The interesting thing about the sensor, it stores a lot of analytical data. One of the interesting things that it stores is the amount of time the sensor operates in a certain pressure range, which is a very unique feature, and it can be used for a lot of diagnostics and performance of the hydraulic system. It also picks up pressure spikes, and that'll be the same with any eye-link sensor. It'll record that pressure spike. It'll record the maximum value it has seen. Another few things to note is M12 cable connection, as I've shown, 1/4-inch BSP process connection, other process connections are available. We're going to stock the 1/4-inch process because generally that is the most common one that I've ever come across and generally used. And if customer needs something else, it's much easier to find a fitting than a pressure sensor. So this slide is a copy and paste from the data sheet. If you want to have a read more and some more information about the sensor, please look at the data sheet and refer to this slide. I'm not going to go into it. And now we go into the next sensor, which is an Iolink EDS 3400 pressure switch / transmitter with a display. So the main thing about this, the reason why I've selected this sensor to keep on the shelf, you can program the sensor via the buttons on board. It has a display. And the cool part with it is you can choose what type of output you want. You can either have Iolink output, as you can see here, or you can have an analog output. Sorry, you can have Iolink and analog, or if you don't want Iolink, you can have a switch output. So it's a bit confusing, but if you have a read through, you'll get an understanding. But that's a nice thing about the sensor. If a customer needs a sensor in a high pressure display, instead of keeping like a 4 to 20 sensor on the shelf, we can now, or 0 to 10 volt and a 4 to 20 sensor on the shelf, we have one that we can customize, and even the customer can customize and select that style of output, all configurable via the buttons. And there's a couple of other features like time delays and things like that on the sensor. So quite a versatile pressure sensor, and I think we will be able to have some success with this. Again, some more information about the sensor from the data sheet. Please have a read through this, and if you have any questions, do not hesitate to let me know. Now we have, moving on to a pressure switch. We have an EDS 820 Iolink pressure switch with no display. So as you can see here, it's a small pressure switch, no display, but the switch points are configurable, and they're configurable via a couple of different methods. So we have programming tools, HPG, which is a handheld programming tool. We have also ZBE P1, which is a programming tool that connects to a computer, and you can program the sensor via that, or a HMG 4000. So this is a nice pressure sensor because a customer may call up and ask, I need a pressure sensor that switches at this point, say at 200 bar and turns off at 100 bar or something like that. And we don't, we may not have that particular sensor in stock, but this one here, we could potentially program it, set it up to the customer, or sell them a HPG tool, and they can program as they like. So it gives them the flexibility and the customizability for future on different certain ways they can do it. So again, a very versatile sensor, and could be used as a really good get out of jail sensor if a customer needs something urgently for a particular pressure range and so on like that. The main thing to note here, this is a PNP output. So it'll be, as I mentioned before, plus it also has Iolink. So if you don't want to use, if the customer also has just an Iolink, they want to connect it straight up, you can use it as an Iolink sensor. But the main thing is, even though this sensor is a pressure switch, if you use it with Iolink, you can read the exact pressure. So the sensor works like an analog sensor, but you can actually read the full pressure range instead of just an on-off signal, which is, but it's a versatile sensor. Again, some more information about the EDS 820. Have a read through that. Any questions, don't hesitate to let me know. Now we come to the non-IO-Link range of a pressure switch. So this is the EDS 8000 pressure switch with the display. Instead of compared to the previous one where you had to program it with a computer or a programming tool, this has a display and programming buttons on top of the sensor, so you can actually customize your on and off points and with the normally open or normally closed outputs, etc., on the sensor. And you can also choose. This one is a PNP. There is an NPN version available, but these are the ones that we're going to stock with. There'll be PNP outputs, and this is the range. So again, also very easy sensor. Get out of jail. You can program the sensor to a particular pressure switch, send it through. And you might have seen in the information that pressure can be displayed in bar, PSI, megapascal. So it's again flexible and could be an option for a customer. Some more information. Now we come to our basic 4-to-20 analog pressure transmitter with no display, no customizability on the sensor. So this one is an off-the-shelf, out-of-the-box sensor and does only what it's intended to do. So if you need a 10-bus sensor, you buy a 10-bus sensor, and the pressure range will be scaled for that particular range. We're going to be stocking the 4-to-20 milliamp versions, and even though there is a 0 to 10 volt option is available, but if your customer needs something urgently, 0 to 10 volts, you can choose the IO-Link sensor with the display where you can configure the 4-to-20 to a 0 to 10 volt output. And then we can work through and identifying something more a long-term solution for that customer. Also M12 connector and things, and so it's a very, very basic standard off-the-shelf sensor. So this will be a very, very common product in the market. Some more information on it. And now just to summarize, these are the sensors that I've just discussed. We have more sensors within our range, and especially for like OEM products and things like that. So don't. If we do need to go to that range, to that product, we can. But these are the sensors generally for everyday off the shelf, and maybe for prototyping use and for the customer to do some testing on, or a customer calls up and needs something urgently, that sort of thing. But for OEM, we can customize. We have other sensor range, and then that's what we discuss. But generally, those topics are more long term, so that's why we have more time to discuss and design something with the customer. But this should be your go-to guide as for particular sensors off the shelf. It's not going to cover every single application and every single scenario, but it should cover a majority of it. Thank you. Now for questions. Andrea Chimodoro. Does HYDAC know the difference in accuracy between a pressure transducer using standard IO connection and IO-Link? The accuracy will be just whatever the sensor has. So on the data sheet, it'll actually tell you what the accuracy is of the pressure sensor from the physical world to the analog conversion, and then that's the only thing they can define, because everything out of that is out of our scope in terms of what cable is used or anything like that. So we can't determine that. It depends on the PLC. Some PLCs, lower cost, may have different particular resolution, and when they're reading an analog input, so it's a very difficult topic to determine. And that is it. Thank you very much for your time, and now I'll pass you over to Mark.
Thank you, Dimitri. That was really interesting, and I learned a lot from that, particularly the new sensors where we've got the combined IO-Link and analog. I think are very exciting. The opportunity for us to be able to integrate much more IO-Link into our product offering is terrific, and some of the deeper understanding about how the different signals are processed. I certainly got something out of that, and it helps us move forward. So by having a market range, something that we can stock and support locally here, certainly availability is a big part of the solution. And I think that it's really important that you understand all the features and benefits from our Australian market range. Thanks for joining us, and thank you again, Dimitri. That was really great, and we look forward to welcoming all of you to our next webinar session. Thanks for now.